Okay, we're on. Okay, thank you. Welcome, everyone. Thank you for coming to our actually last but one. We have technically another seminar next week. And it's a pleasure to have here Professor Hero, Alfred Hero from University of Michigan. I'm going to make the introduction very brief because if I actually try to introduce Al, it'll take me the whole hour, so I'm not going to.
You have that many bad things to say about me?
I'm not going to. So Al is currently the Jamison and Betty Williams Professor of Engineering at University of Michigan, of course. And he also has a position that takes him to France every year for a couple months, digital chair at the Digital Research Institute in France, southern Paris to be exact. And at the University of Michigan, of course, he is a professor in electrical engineering and computer science. And he also has secondary appointments in the biomedical as well as in the statistics department. He's also affiliated with the University of Michigan program in biomedical science and the graduate program in applied interdisciplinary mathematics at the University of Michigan. Al has basically held every position you can imagine within the IEEE hierarchy. He's a fellow, of course, of the IEEE, and there are many, many other titles which I don't have time to go through. And it's a pleasure to have him here. Thank you. The floor is yours.
Well, thank you for inviting me to talk to you today. I am especially happy to be in a part of the country where there's sunshine and the weather is above 30 degrees. So I'm going to talk today about a fundamental problem, and that is how do you decide whether a correlation that you read about in the papers or that you discover in a set of variables is for real, right? And surprisingly, this problem has not received a lot of attention because there's a lot of work out there which claims high correlations and uses correlation as a method to extract structure from interacting variables like in genetics, gene expression, or in finance with financial instruments that co-express, if you like, in their bid prices. But there's really an absence of theory to tell you just how many samples you need in order to be confident of these kinds of statements that are being made out there. And so I hope at the end of this talk you'll see that it is possible to construct a very general theory of correlation screening, and more particularly screening for other types of structures in correlation graphs of interactions between variables, in particular hubs. So this work is joint with my colleague Bala Rajaratnam in statistics at Stanford. And so what I'm going to do is I'm going to start out with some motivating examples which put some flesh on this comment that I made before about the popular press being full of correlation statements with perhaps limited amount of validation. And then I'm going to talk about graphical models, which is one way of describing correlations between a lot of variables in a mathematical way. And then, given that description, we're going to talk about screening for hubs, effectively just by deciding when sample correlations that have been measured from empirical data exceed a threshold, which is the standard method that's used in the motivating examples. And then I'll talk about persistent discoveries, that is, discoveries of correlations that exist at one time and also at another time, or in one treatment and another treatment. So that's basically what the outline is. So here is one example taken from the Futures magazine, a magazine, electronic magazine that is read by a lot of stockbrokers and financial quants. So what I'm showing here are two historical records of the spot World Trade Index for oil and the dollar index. And this is, extends over a period of about 2.5 years up to February of 2010, right after the Greek debt crisis hit. The title that was attached to this picture in the magazine was that we are entering a period of divergence between the correlation between these two historical indices that have been basically negatively correlated in the past, but when the Greek debt crisis occurred, all of a sudden we're positively correlated. Okay, well, visually, that may or may not be convincing to you. I mean, for example, I can find other regions where it looks like there might be some degree of positive correlation back here. But this was the claim. And it's based on, you know, a number of maybe 20, 25 samples of daily closing prices or exchange rates or what have you on these historical indices. So the question is, how much confidence can we really have that there's been a shift in correlation here? Statistical confidence. Is a period of a few weeks enough to say that we really are in a period of divergence? And that's the answer to that question is going to be predicated on a hypothesis, which is fairly strong, one could argue, that we have statistical independence over these samples. And if you don't have statistical independence, then it's even more tenuous, right? That you can state that you have a divergence in the correlations. All right, so this is for two records, two variables. And one can apply a Wilks sphericity test or other types of statistical tests to test whether this has occurred, whether there has been truly a divergence at this point, and come up with like a p-value, a probability that that there hasn't been a change in correlation. So we can extend this to more than two records. So here are 14 exchange rates or exchange rate spreads between different world currencies, and this is taken out of another blog, which is financialbootcamp.com, and what this blog basically claims that correlation matrices are essential for deciding where to put your money, right? And so if you're worried about the exchange rates, then you want to look at those exchange rates that have a high correlation, high positive or negative correlation, and then hedge on that basis, right? So what we're interested in is, if you're going to put your money on a particular instrument, then you want to put your money on an instrument that has, say, low correlation with everything else if you want to diversify your portfolio. So you want to avoid putting your money on these other instruments that might have relatively high negative or high positive correlation, right? So that's the argument that this blog was making. Now with 14 time points, these are averages that produce these ellipses that sort of a cartoon representation of correlation over only 20 samples, right? Basically a month's worth of data. And the question there again is, how confident can we be if we choose one of these exchange rates to hedge on, that exchange rate really doesn't have significant correlation? Or conversely, if we're trying to avoid one, that has strong correlation, how confident can we be that based on 20 observations we can really pull out one of these exchange rate spreads as having high or low correlation? Okay, we can represent this this correlation matrix as a graph, and here I've taken 100 variables with only 25 samples, and this is a thresholded correlation matrix, right, between the 100 samples, the 100 variables sampled at 25 different times, if you like. And then if you look at each one of these correlations that exceeds the threshold in magnitude, let's say, you can draw an edge on a graph between these vertices that correspond to the different variables. And so graphs and thresholded matrices are equivalent. That's all I mean to show here. So talking about building a level of confidence on a particular variable having high correlations with some other variable is the same as building confidence on a particular vertex of a graph having, say, high degree, right, being connected to a lot of neighbors. Taking this to an extreme, here we have a case of spammers. There's 10,000 IP addresses which have been, through honeypot attribution, declared as spammers. And one can then render a correlation graph like this by thresholding a 10,000 by 10,000 correlation matrix, and then start asking questions about structures of the community of spammers. That we have this big group here which are basically all connected together in a big bunch. We have a few out here that look like they're behaving a little bit differently in terms of correlation, temporal correlation in this case. This is time measured in terms of days. And this is the number of emails sent by each one of these IP addresses to a spam trap, right? And so here, but visually you'd say, well, these look pretty highly correlated. And this actually corresponds to this little group here. But how about some of these others in here? Are they as significantly correlated? And how well can we depend upon our visual inspection to be able to tease out that these 5 separate variables that are denoted here in time are actually sufficiently correlated so that we can be confident of the vertex degrees of each one of these variables, these spam IP addresses. Here's another example. Came from a blog by a financial quantitative analyst, which is behind a lot of the news you hear today about the financial sector. Used to be you had a relatively low correlation between different sectors, and today it's much higher. So you hear things like 80% of all of the stock indices are correlated today, whereas historically it's been, the correlation's been under 50%. So in terms of diversification, it's a big thing, right? A big issue. This claims to instantiate this using a correlation graph. So this is before in January, and this is after. So the question is, do you have a degree of confidence in this change of correlation over time? So what's the problem?
That's over a span of months?
That's over a span of months, yes. Right. So that was a 2 or 3 month average, and comparing 2 different quarters, 2 separate quarters. Yeah.
But what does the 2 horizontal and vertical axes mean in your plot?
Which one?
This one.
This one here?
Well, actually, both plots, yeah.
Well, this is a index of sampling time. So that's every day you get a number of emails from IP address 1, 2, 3, 4, 5, and this instantiates the number of emails that you got. And which other XY axis? This one?
The next plot.
This one?
The one with the circles.
Oh, that's nothing. These axes don't mean anything.
Oh.
Yeah, this is just a, like this graph, oops, that I showed, is just a rendering of a graph to show what the interconnections are. A visualization device. Yeah.
And what are the connections in the graph he was just referring to? In two slides from now? What are the connections in this graph?
Yeah, so these connections are correlations over time.
Okay.
So here it's over 80 days for this picture, oops, and 60 days for this picture. And so it's just like this, right? Just like for the spammers. So they measure correlation by temporal correlation of the actual indices that correspond to each one of these sectors. So here's the problem. The problem is when you look at correlations among a very large number of variables, there's a phase transition phenomenon. And so if we look at the number of discoveries of connected vertices, what do I mean by that? Well, go back here. The number of rows of this correlation matrix that has at least one entry that exceeds the threshold in correlation value, excluding, of course, the diagonal axis, which is the diagonals, which are self-correlation variances. So if we look at that, which is the number of vertices that are connected, and we look at raising the threshold, so you're going to discover more of those vertices as you lower the threshold, fewer as you raise the threshold, right? Then the threshold will determine when you get a large number of discoveries, when it's relatively low. So this is the correlation threshold. This is the number of discoveries. And you'll get virtually no discoveries if the threshold is sufficiently high, right? Because all the correlations in your correlation matrix lie below that threshold for a sufficiently high threshold. So this is a phase transition because we get a very rapid degradation of our test for true correlations in a set of here 100 variables where these 100 variables I've simulated with zero correlation. So there's actually no correlation here. But for a sufficiently small threshold, there are going to be spurious sample correlation values which will exceed the threshold. So, and it very, very rapidly exceeds the threshold and produces, a lot of discoveries. So, as you decrease the number of samples that are available to estimate this correlation, the set of sample correlations, the phase transition threshold gets more and more punishing, right? It means that we can no longer be confident that if we discover some correlations in some, let's say, are greater than 0.5, that those correlations, that those vertices actually correspond to true underlying correlation. They could just be spurious correlation because that's all there is here, right? Yeah.
So in these diagrams, we generate statistically independent variables. Is that
Yeah. Everything it's all diagonal correlation. They're Gaussian variables. So there is no structure. There is no correlation structure. Every vertex in that graph is isolated, right? No edges. And so you can see as if you use only 10 samples with 100 variables that you're squeezed almost arbitrarily close to 1 in terms of being able to detect true correlations. So what this says is that if someone tells you that based on 10 days of averaging daily closing prices of 100 stocks that the correlation is 0.8, well, it's hard time believing that, right? Now, if he tells you the correlation is 0.99, well, that's reasonable, right? So the whole point behind this work is to give a mathematical characterization for these phase transitions. And if we can do that, then we can predict as a function of the number of samples, the number of variables, the phase transition threshold, the thresholds that we apply to the correlation matrix, what the critical threshold will be, right? That'll be important. And under general assumptions of sparse correlation graphs, that is, correlation matrices that only have a relatively small number of non-zero entries. So they're sparse in a sense that I'll make more clear in a minute. Okay, so I've talked a little bit about correlations. There's an important distinction when you talk about sparse dependency models, and correlation is one type of dependency. There are really two types of models that one can be concerned with. One are sparse covariance graph models, and covariance graph is what I've been showing you before. Just show the edges as present if the covariance, or actually the correlation coefficient, sample correlation coefficient between the two vertices that the edge connects exceeds a threshold. And then there's also what are called concentration graph models, which instead of thresholding the correlation, the sample correlation, will threshold the inverse of the sample correlation, something called the partial correlation. So what the sparse covariance graph models detect or are matched to are things like M-dependent processes, where if you have a time series that after 10 days there's zero correlation with what came before, right? And moving average processes is one example of that. So there are few marginal dependencies. Most covariance entries are equal to zero. Concentration graph is a different type of dependency model, where we're saying that there are a few conditional dependencies. Conditioned on what? Well, I'm going to talk about this in a minute. It's conditioned on all the neighbors. So you say the two variables have a partial correlation equal to zero. That means that the correlation, the conditional correlation between those two variables, given all the other variables, is equal to zero. Okay, so it's an independent, a conditionally independent type of assumption, as opposed to a marginally independent assumption. And examples here are Markov random fields, autoregressive processes for which the inverse covariance is sparse, but the covariance itself is not sparse. So there's some data that can be simultaneously sparse in both domains. For example, block diagonal covariance structure is sparse both in the inverse and in the covariance itself. And some are sparse in only one or the other. And our theory applies to both. The graphical models are a case where, as I say, we are basically ascribing patterns of conditional dependency among a set of variables, right? As opposed to patterns of correlation or conditional, unconditional correlation. It's patterns of conditional correlation. And so if you, in the general setup, you can go beyond correlation and talk about conditional independence, pairwise independence, conditioned on all the other variables. So the conditional probability distribution of two variables, given all the other ones, factors into the product of the conditional distributions. And this is equivalent if you put an edge between these two variables. If they factor in this way, if they're conditionally independent, you don't put an edge between them. You only put one if they are conditionally dependent. Then this factorization property is equivalent to a factorization of the marginal distribution. So graphical model basically gives you a factorization of the joint distribution over a graph, right? So that's what these graphical models give you. That's why people like these graphical models when you start talking about large graphs of interacting agents, because a graphical model like this depends, will put edges only where there are conditional dependencies and not marginal dependencies. So, the idea being that, if you're looking at a social network, for example, and everybody in the social network has some common interest, right? If you don't condition on that common interest, everyone will look correlated, right? So if you do condition on it, then you can decorrelate that factor from the population. And if everybody has that factor, then conditioning on most of the population is equivalent to conditioning on that factor, right? So that's one of the motivations. Now, for the Gaussian case, we have what's called a Gaussian graphical model, where this factorization property is specified by the inverse covariance matrix K. And that's called the precision matrix or the concentration matrix. And we can define this adjacency matrix associated with the graph, which describes which pairs have edges and which pairs don't, by hard thresholding this inverse covariance. The zeros in the inverse covariance will be places places in the graph where there is no edge between the corresponding vertices, and so you can use a hard threshold function like this, which pulls out a 1 or thresholds to either 1 or 0, depending upon whether the inverse covariance has a 0 or a non-zero. Okay, so rho here is an arbitrary positive threshold. So that's what we're varying in those phase transition plots, right? Now, an equivalent representation is through the partial correlation matrix, which is taking the inverse correlation and normalizing it so that the diagonals are equal to 1. And this partial correlation has the same zero structure as the inverse correlation. So one can equivalently threshold a partial correlation to come up with a graphical model as one can threshold the inverse correlation. And then one gets, by doing this, you can get a taxonomy of different types of graphical models, like this block diagonal case, which corresponds to 2 cliques in the graph being separated, no edge between clique 1, 2, and clique 3, 4, and 5, because there's no correlation between them, right? You have coupled cliques that look like this, where you have a separator, where if you condition on the separator, you separate into 2 uncorrelated components these 2 cliques, 1, 2, and 4, 5. Right? And you can have multi-scale types of graphical models that reflect this kind of hierarchical structure, hierarchical correlation structure, where conditioned on 2, 4, and 5 are uncorrelated. Right? Okay, so with that in mind, what we're going to be interested in doing is finding hubs in a correlation graph, either a correlation or a concentration graph. And so hubs are basically star components, right? So in the zoo of possible non-isomorphic subgraphs that you could possibly find on, up to 5 vertices, 6 vertices here. Star components are what we're going to focus on. We're going to look for those components in the graph, and we're going to try to ascribe the to each one of these components a phase transition type of behavior. Right? That's what's on our docket here. So I'm going to be dealing with 2 different types of situations. One I call single treatment. That's just when we have a single graph, and we're looking for these hubs. So I'm going to look for vertices indexed by I, for which their degree is greater than some specified degree d over all the p variables, and that's will give rise to n of d. So that's n the number of hub nodes in the correlation or a concentration graph that have degree at least equal to d. And with different treatments, we're going to be looking for the number of hub nodes of at least degree d that remain under two treatments. So like in that example I was showing you of this correlation between these financial sectors over a period of two quarters in the year was showing a change. This would count the number of sectors for which the correlation structure, the hub degree, was not changing under those two conditions, right? Under both quarter 4 of 2010 and quarter 1 of 2011. So these are two problems that we're going to consider. And so the first thing is to define the sample partial correlation matrix. So K in what I had showed before in this Gaussian graphical model is the theoretical inverse correlation matrix, right? Or inverse covariance matrix. We don't have access to that. All we have access to is n IID samples of this p-variate quantity. So you measure the indices of these financial sectors as a vector of p quantities n times over some period of a quarter throughout the quarter. And then we're going to threshold the sample partial correlation matrix, which is defined, I give it nomenclature P, as the analogous normalization of the inverse correlation, but so that the diagonals are equal to 1, right? And this is sort of the sample correlation defined as the ratio of the covariance estimate divided by the product of the variances of each pair, square root thereof. Also can be expressed, of course, as in matrix form through a Koleski factorization, as it's so called, or Bartlett decomposition of the covariance matrix. Yeah.
Is there any reason why you multiply by the inverse diagonal to the 1/2, and not by simply the inverse diagonal itself?
Right, because you have to do it on both sides because P has to be symmetric.
Okay.
Right. So if you only did it on one side, then you would produce a non-symmetric correlation matrix.
Okay.
Right. That's why we have to do it on both sides with a factor of 1/2. Yeah. All right. So the issues here is there's several difficulties. First of all, in all the examples I showed, there's many fewer samples than there are variables. So the inverse of the sample covariance doesn't even exist, right? The sample covariance is only rank n, but it's a p by p matrix. So there's no inverse. So that's the first problem, which is a pretty bad problem. But even if we did have enough samples that to make the covariance matrix, the sample covariance matrix invertible, we're going to get false matches for any applied threshold level because of this phase transition phenomenon. As long as that threshold level is not precisely equal to 1, there's going to be some probability, maybe very small, of getting a false match. And we have this phase transition behavior. So what we're going to propose here is, first of all, for the sample covariance matrix singularity problem, we're going to find a rank deficient version of the partial correlation using a pseudo-inverse instead of a ordinary inverse, the Moore-Penrose pseudo-inverse. And then we're going to derive finite sample theory that will tell us what the probability of getting false matches are given a sample. And then we're going to give expressions for phase transition thresholds and apply this to correlation graphs, concentration graphs, and so forth. So the key behind the mathematics of being able to tease out the form of these critical phase transition thresholds is something called a z-score. So for those who have taken classes in statistics, you know a z-score as sometimes it's called sphering the data, right? You have some data vectors and that are, say, IID samples, and you basically subtract the sample mean, divide by the sample standard deviation in order to get a set of samples that have 0 sample mean and unit sample variance, right? So that's the z-score. Now, a z-score is important because when we're talking about correlation coefficients or partial correlations coefficients, that is the entries of those two matrices, it turns out that the z-score is the covariance of the z-score is equal to the correlation coefficient, right? So if you work with z-scores instead of the original data, the sample correlation of the z-scores is equivalent to the sample correlation coefficient, right? The normalized correlation that takes values between -1 and +1. So we define a matrix of z-scores simply by stacking these vectors. This is for one particular variable I, right? So one particular sector, financial sector. We stack them into a vector of length n, and then we pile them all up in columns, and we have an n by p vector. Unfortunately, that n by p vector is n by p matrix is rank deficient. Why is it rank deficient? Because we've removed degree of freedom here by subtracting the mean, and therefore we have to reduce in order to have a non-rank deficient equivalent set of z-score measurements. We have to reduce the number of rows by 1. So this becomes an n-1 by p matrix by doing that. And these so-called projected z-scores lie in the sphere. They lie in a sphere of dimension n-2 because we removed one degree of freedom by subtracting the mean, which basically means that the vector of these z-scores is orthogonal to the unit a unit vector pointing along the diagonal, right? A vector with all ones divided by 1 over root n because we subtracted the mean, so it's orthogonal to any constant vector. And it also lies in the sphere because the norm squared of this of that vector is equal to 1. So it's a sphere of intrinsic dimension n-2 in a n-1 dimensional space. So with this, the sample correlation matrix can be represented simply as a product of the matrix of projected z-scores transpose times itself. And so the ijth sample correlation is simply the inner product of the ith and jth column of this matrix. And we have a similar z-score representation for the sample partial correlation, which I'm not going to go into. But we have a similar type of what's called a gram representation for the correlation, an inner product of vectors. So let's do some experiments on these z-scores. So I've simulated Gaussian data with 500 variables, diagonal covariance, and this is for n equals 4. So we remove the degree of freedom for the mean. It's on an n-2 dimensional sphere. So n-2 when n equals to 4 is equal to 2-dimensional sphere, so that's what we see, right? So when I render these z-scores, I see that indeed they look like they're on the sphere of dimension 2 embedded in a space of dimension 3. And these 500 different variables, even though they're completely uncorrelated, some of them appear to lie close to each other. Now, what does it mean that they lie close to each other? It means that they have high sample correlation, right? Because of this inner product relation, right? High sample correlation if the two vectors, right, centered from at the origin of the sphere and ending at this point and that point, have an angle which is close to 0 degrees or 180 degrees, since we're looking at magnitude correlation. So there's going to be some spurious sample correlations that exceed any threshold, which is greater than the minimum distance, or the maximum inner product, I should say, between any two of these points. Now, it also looks like these are uniform over the sphere, and there's no accident to that. In fact, it turns out that there's a well-known theorem that is in T.W. Anderson's book on multivariate analysis, which says that if you start out with a Gaussian random sample with a diagonal covariance, then the z-scores will have a uniform distribution over the sphere and be independent, statistically independent. So what happens if you don't have a statistically independent, that is, a correlated structure? So here, this is an ARMA 2 correlation matrix. So I have a time series of Gaussian distributions simulated from the Gaussian distribution, where I have an ARMA model that's generating these variates xi. I have 500 of them, and you can see if we have 500 points in time successively increasing, this would correspond to more and more variables becoming highly correlated with each other, right? More and more time instants being highly correlated. The correlation effectively extending over a longer window as time increases. And for this, if you look at the z-scores on the sphere, they're highly clustered. So the question is, of course, can we distinguish between a picture like this and a picture like this? Well, clearly we can in this case, but because we have such a large difference between the diagonal case and this case of an ARMA 2-2. But in general, can we be confident that this isn't just a realization from a diagonal covariance matrix, right? So that's the whole point that we're going to address. So hub screening has to do with finding variables on this sphere, these z-scores, such that if you apply a threshold rho, rho defines the radius of this cone that I'm showing here, that on the spherical cap that is defined by this cone, that there's at least one other variable that falls into that region, right? So that in that case, we would have connectivity. If you're looking for a hub of, say, degree at least d, then you want to find points that have at least d neighbors in this spherical cap, right? So that's the intuition, and therefore we can now use that to develop a phase transition theory. So first thing we can say is, what if the points, the z-scores on the sphere were uniform? Well, then the probability of getting, at least one neighbor within this region would be easily calculatable. It would be the area of this spherical cap of radius rho, actually square root of 2 times 1 minus rho, divided by the area of the sphere, right? Actually, since we're looking at both positive and negative correlations, you have to include both caps. So it's twice that quantity, that ratio. That would be the probability of getting a spurious detection of a connected component, or a connected vertex, I should say. It would be the probability that within this radius centered at one point, we would find at least one other point. That's an easy calculation. So that's basically what's behind the theory that we develop. So we define the number of vertices having degree greater than delta as n delta rho, and it's the sum of a set of indicator functions of whether or not the point I has at least delta neighbors in that little spherical cap of radius square root of 2 times 1 minus rho. Here z is my notation for z-score, either for the correlation or for the partial correlation. So we have a theorem. And the theorem says, it's a very strong theorem. It says that no matter what the true underlying distribution is, As long as as the distribution of these variates is, these p-variates, joint distribution, is a continuous distribution in the sense that there are no atoms, there's no points of concentration, it's a Lebesgue continuous distribution, that the limit of the number of these discoveries, n, is Poisson. So there's a Poisson limit with a rate constant, lambda, which is given by an expression that depends upon this ratio of the area of that spherical cap divided by the entire area of the sphere, which is this p0 quantity. Depends on n, because that's the dimension, fixes the dimension of the sphere. Depends on rho, because that fixes the radius of that cap. And it depends on delta, which is the Hubble degree that we're looking for. And of course, it depends on the number of variables, p. It also depends on the underlying distribution in general, except here we're assuming we have a sparse graphical model. So either the correlation matrix is sparse, there's only a few non-zero entries, big O of p, or the partial correlation, the true partial correlation matrix is sparse. In that case, this Poisson limit is universal in the sense that it applies to arbitrary distributions that specify dependencies between these variables. So it's, this is the theorem, and this just describes the sparsity notion that's used here. We require sparsity in the sense that there exists some permutation of the rows and columns of the matrix that brings it in a block diagonal form. That's when this universal limit holds. Okay, so why are we interested in universal limits? Well, because to be practical, in order to go out there into the field and say to a potential investor that the blog that he's just read is reliable under the assumption of some sparsity on the correlations, we need to be able to make that statement without referencing a particular assumption of the correlation structure, precise correlation structure of the problem. So we can very easily get theoretical mathematical expressions that we can use to describe the phase transition phenomenon mathematically. And so here is a function of the number of observations. Here p is equal to 10, the number of variables equal to 10. Here it's equal to 10,000. We're using just connectivity, so delta equals 1. We're looking for at least one connection. And so what you can see is as you apply the threshold, if you have a lot more measurements than you have variables, so you're up here, that you can apply a threshold anywhere in this region and be guaranteed that you have few false discoveries, right? And as the number of samples decreases, that critical threshold gets larger and larger until eventually it hits 1. Now if you go to 10,000 samples, this phase transition threshold gets more punishing, right? It moves to the right. Now I can take a slice of this picture and shows here for several choices of n. So I'm just taking this heat map where color encodes the average, the probability of false discovery, and I'm plotting that now on a scale of 0 to 1. And so we can see here again for only 6 samples, we're basically up against a phase transition threshold which is basically 1. So there's no hope with 6 samples, and here 500 variables of being able to say anything intelligent based on thresholding the sample correlation. If, on the other hand, we are significantly higher samples, like on the order of the number of variables, 500, then we have a very large range where we can be confident of very low false positive rate. The critical threshold has a mathematical formula for large p, which is given down here. And this threshold has the interesting property that if n is large, then p to the minus 1 to the to this power, basically the n minus 4th root of p minus 1 looks a lot like a log of p, right? So for a large n, the phase transition threshold increases towards 1 at a logarithmic rate in p, which is, you know, a slow rate, a good rate. For n small, we get a much more punitive rate, and you can see that in these two pictures. We can also look at as a function of the of delta, the vertex degree. As you increase the vertex degree, you get better and better phase transition behavior. So here we're in for p equals 1 billion. Here's the phase transition thresholds. Here I think we're using number of observations from 1,000 to 100, 0 to 1,000. So we have a very nice and rapid decrease of the phase transition threshold for even for 1 billion variables. Right? You don't need anywhere near 1 billion measurements in order to make reliable decisions out here about correlations being false positives or not. And as you're looking for higher and higher degree, vertex degree, that threshold gets better and better because it gets much less likely that a high degree occurs in random diagonal covariance matrix, which would produce random edge connections, right? Well, we have convergence rates for these theorems. I'm not going to for this theorem, and I'm not going to dwell on this. I can also explain where the Poisson convergence rates come from. I'm not going to dwell on that either. But I will tell you we can use this theory to produce very useful tables like this. So this is a table that you can give to an experimenter or a financial quant or an investor. And he can say, okay, that divergence phenomenon was predicted with 20 observations. I want to make sure that with confidence level of 1% false discovery, that I can detect a correlation of at least 0.88. Right? So you look at this is the entry that tells you then use 0.87 as your correlation threshold, and you can detect a valid correlation at 0.88. And this is the valid correlation calculation is made through something called a Fisher Z Gaussian approximation when you have a spike-in model where there's a single correlation, a single non-zero correlation. So this is a very useful table for obvious reasons. The simulations here are just show the theoretical versus empirical performance predictions are right spot on. So these triangles, these diamonds are the targets that we've specified. We use the table to design the thresholds for various numbers of observations, 1 through 6 observations, and we're very, very close to the ROC curve, the ROC characteristic with using this theory. So the theory allows you now to set these thresholds for a guaranteed rate of discovery. So I'm going to show you very quickly just a couple of data sets that we've used. Mainly these are gene expression data sets. Here p is equal to 24,000, which is Affymetric's version of the human genome. Whereas 295 samples are subjects, and what we're looking for is a correlation structure within these 24,000 genes, right, that will reveal hubs that have high confidence. So what we can do is we can first of all use the theory to predict the phase transition threshold for this example, and it's quite small. It's 0.3, so we could discover theoretically significant correlations greater than 0.3 given that we have 295 samples with 24,000 genes. And then what we can do is we can compute p-values, which are the probability that we would observe a certain number of false positives, given that there was no correlation, right? And so the first thing we can predict, we look at a sham where we've removed all correlation by basically permutation, random permutation of all of the variables. And so we now have a sham set where there is no correlation, and we can see that the number of predicted discoveries, the mean number of discoveries, is quite close to the actual number of discoveries. This is just one simulation, one run of a simulation. It's quite close for a single run. This shows what we call a waterfall plot of p-values. So this is for the sham set, and each one of these is basically a trajectory of nodes in the graph that have hub degree greater than or equal to 1. And how far down this little finger goes, it gives you the p-value, how significant. So more significance goes down this way. So this hub, this index that specifies that particular point is highly irregular in this data in the sense that it has a fairly low p-value for having that much correlation, given that this is a random set of data. Now, when I say highly significant, that's not really true, because this is the log of the p-value, and that's only 0.5. This is the real data, and so you can see that for degree 1, 2, 3, 4, 5, and so forth, we get this really comprehensive summary of 24,000 variables, and we can pick out those variables that are the most significant in terms of their hub degree behavior. That is, they have behavior which is incompatible with an assumption that there is no correlation. And this is just another rendering of that. So what I want to do, I think, is probably just skip this part and go to the conclusion, since we're late. So the part that I skipped was extending this theory to discovering persistent hubs that persist over multiple treatments. So we have a similar type of theorem that allows us to set thresholds and to define what the most significant variables are in terms of persisting over several treatments. So insufficient number of samples will imply that you're going to have a sharp phase transition threshold, which is going to be punitive. It's going to be close to 1, so you won't be able to make many true discoveries. And you cannot trust cross-validation and bootstrap in these situations. With a very large number of samples, just by chance, the probability approaches 1 as the number of variables increases. The probability approaches 1 that you will get spurious sample correlations no matter how much cross-validation you use, right? No matter how many leave one out samples you extract and recompute the sample correlation, just the fact that we have so many variables, you're going to get spurious large sample correlation. So data-driven methods just can't be trusted in these very large sample situations. You have to use some mathematics, some models, in order to predict what the intrinsic probability of a positive discovery would be in terms of the correlation graph, for example. The references, there are 2 papers. One of them is going to appear in JASA any time now, and then the other one has been submitted and it's on the archive. So that's all I have to say today. I'd be glad to answer any questions if there are any.
Any question?
Yes.
So I'm wondering, you have a correlation matrix that you estimated based on real data. and you want to use that correlation matrix for some purpose.
Right.
Now, clearly, if the correlations are small, one would imagine that they're spurious. If the correlations are large, one would imagine that something's really there.
Right.
So how would you, for a typical purpose of using a correlation matrix, how would you manage to shrink it to? Would you suggest to shrink it toward 0? What's your proposal?
Yeah, so that's a very good question, because the whole motivation for this was on doing inference on the correlation or the inverse correlation. I didn't talk at all about how you would use it afterwards, if you will use it, to do inference, like regression or prediction or classification. So this can be viewed in one context as a method for variable selection. And one can hope that variables that are selected that have high correlations would also be effective variables in, say, performing prediction, right? But then there's also the problems of multicollinearity that enter. So some of the variables that have high correlation may have high correlation because they are basically they contain redundant information. They don't contain the independent information, so you might not want to use both of them in a predictor. So if you're interested in a parsimonious predictor with the minimum number of non-redundant variables, this theory is not going to give that to you, right? But it will give you a superset of variables that are highly correlated that would normally be included in such a predictor. Now, we have extensions of this theory which haven't yet been published. We're still actually writing up the theory now, which specifically applies to prediction. So instead of applying this theory to the sample correlation or sample inverse correlation, we apply it to the regression coefficients, which is a product of the sample cross correlation and the inverse correlation, right? And so now turns out you can apply the same theory, but with some modifications to that problem where you explicitly take into account what the final purpose of the inference task is. Does that answer your question?
Sort of.
More or less?
We can take it offline and
Yeah.
discuss later.
Yeah, okay.
So I'm thinking of a potential application to like PCA. If we have small number of samples, can we, if we first threshold it according to how many samples we have and what dimensions they are,
Right.
and then do a PCA, do you think we get better results according to what the...
Better, it depends on what you define like better, right?
I mean, if we already know what the principal component is and we have small samples.
Yeah, I mean, it's an interesting question. I think that clearly, if you had sufficient number of samples so that you could put that critical phase transition threshold down at 0.2, 0.3, then I would say that would be a good application. If you have 6 samples and 100 variables, then it's not very good because the critical phase transition is only going to pick up very high correlations. There may be some moderate correlations that are equally important in the PCA, but that you just can't find because they're buried in the phase transition mass, right? Which means you can't distinguish a false correlation from a true one. So my answer is yes, this would be applicable if you go and use the table that I showed you to figure out what the sufficient number of samples is to get a low phase transition threshold, and then you can shave off the variables that don't pass that threshold as being putatively with a level of significance given by the theory, not involved in the latent variable that controls the model, right? So they wouldn't appear in a PCA, first few components with large weights, right? Yeah.
Quick question. How
Yeah.
is this related to the work by Penrose and all his,
Yeah, that's a great question.
collaborators?
Yeah.
Is this more for the small sample scenario, or what?
Well, Penrose didn't study correlation.
Well, but he
phase
did.
transition threshold.
But
What he has studied,
But he
he's
uses
looked at
percolation models. Where,
right,
yeah,
right, yeah. So this is related to Penrose, and it's related to Penrose work in a very close way, and that is that if you look at the asymptotic Poisson limits that he gets for his ball graphs over a Euclidean space, that's related to the limits that we get here for ball graphs over the sphere. That's the difference. Is it his methods aren't exactly transferable to here because he assumes a Euclidean structure on the variables that he measures. But if you're interested in correlations as opposed to covariance, then his theory doesn't apply. So you need to use something else, and that's what we apply here. So, but the methods that he uses are based on something called the Chen-Stein or the Stein method for convergence. It's sometimes also called the law of small numbers. When you have few but rare events, limits towards the Poisson as opposed to laws of large numbers like the central limit theorem. We use similar machinery in order to prove these limits. So in that sense, there's a tangency. Yeah. But he doesn't study phase transition thresholds or inference procedures for graphs. Or,
No,
yeah, right.
I
Yeah,
was-
yeah. But
I was
it's good.
fishing more for the,
Yeah,
the
for the
link
mathematical
between, yeah.
link. Yeah, and that's it. Yeah. Yeah.
Well, if there are no more questions, let's thank our speaker again.